Hello, this is Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video is part 2 of the video lesson on thermodynamic property calculations for real substances. In the previous lesson, we had developed these mathematical rules, and we have a reciprocal rule, a triple product rule, and a second derivative rule. We use the second derivative rule to develop Maxwell equations. The triple product rule and the reciprocal rule we haven't really used yet. So let's start looking at how that combines with our Maxwells. Now this is what most people consider the full set of Maxwells. These are written on an intensive basis for a pure substance. So we don't have to worry about the N, okay? No change in number of moles in this case. And so this is what you would get if you looked at each of the energy functions, all 4 of them. But what we want to do is we want to consider which of our variables are measurable. So I look at this and it's like P and T, volume, I can do those, I can measure those. But internal energy, enthalpy, I've got a whole bunch of these things that I really don't know how to measure, okay? And worse than that, if I have something like H, it's a function of S and P, well, I can measure the P, but I can't measure the H, and if it's I can't measure the S, and if it's a function of it, how can I go any further? So what we want to do is we want to start looking at things in terms of measurable quantities, things so that we can actually evaluate what these various functions are. So we're going to use our math tricks, our definitions of fundamental relations, our Maxwell equations, and those math skills in order to come up with things that we actually can determine experimentally. So our measurable quantities, pressure, volume, and temperature. But we can also measure C sub P or C sub V by looking at energy changes, heat transfer basically, through a constant pressure process or a constant volume process. And we can measure changes in volume as we change temperature or pressure. And these compressibilities, how volume changes with temperature or pressure, are things that are measurable and occasionally for some substances recorded. So this is going to be our list of measurable quantities. So we're going to want to translate changes in a variable, so H for instance, into things that relate to just these quantities, things that we can measure. So let's look at H, which in terms of natural variables for a pure, and we'll call it a closed system, is a function of S and P only. We'll ignore the change in N as a possibility. What we want is to know how H changes maybe with T and P, because T and P I can measure. I feel real confident in my ability to measure those. Now, if I do this and start saying, well, wait, I know how to use the definition of a differential. dH is dH dt at constant pressure times dt, plus dH dP at constant temperature times dP. In terms of measurable quantities, dH dt at constant P is C sub P. But what about this dH dP at constant temperature? That's not in my list of measurable quantities. So let's start with this dH equals TdS plus VdP. Okay, back to the fundamental relation. And what we're wanting to find is use this to figure out what is dH dP at constant temperature. That was the question that we had from the previous slide. But I can use this with the fundamental relation to say that, this is equal to T times ds dP at constant temperature, looking at the same change, plus V dP dP at constant temperature. Now, this first grouping maybe is not obvious to you what that means, but the second one, dP dP, how does pressure change with pressure? Well, that's 1. So this is equal to T ds dP at constant temperature plus the volume. So far so good. I know this one. I still have this ds dP at constant temperature. So what is that? Well, go back and look through your list of Maxwell's. And sure enough, we have one that says that, oh, wait a minute, ds dP at constant temperature is negative dV dt at constant pressure. That's one of my Maxwell's. So therefore, dH dP at constant temperature is negative T dV dt at constant pressure plus the volume. So now everything here is in terms of things that are measurable. All right, so in our previous slides, we had found that dH is equal to C sub P dt plus dH dP at constant temperature dP, rewriting H as a function of temperature and pressure. And the dH dP at constant temperature we now have seen is equal to V minus T dV dt at constant pressure. If we want to use that isobaric compressibility, beta is 1 over V dV dt at constant pressure, then we can say that dH is Cp dt plus V minus beta Vt dP, just using a little magic of rewriting things. So this concludes this example. We'll be doing more of these in class and in future lessons. Thank you.